Welcome back, everyone. And we're delighted to have Dragan Milicic, who is visiting us for several months, talking about something to do with GK modules and D modules. Thank you, Dragan.
Thank you. So I'm doing this just as a public service because I got a list of topics for Dougal he would like that I discuss. And we have this seminar on D modules. So I knew that there will be some students present. So I want to see how far I can go on Dougal's list. So first, I want to review some general basic facts about localization, which we discussed in our course.
Right, big, Dragan.
Oh, bigger?
That's lower down.
Okay. So first, I will start with a completely algebraic situation, and then I will get to Harishchandra modules, which are defined by Dougal. So let G be simple the algebra. Everything is over C, and U of G is its enveloping algebra, and Z of G is the center of UG. Let's denote by X the flag variety, G, so the variety of all Borels of G. And let's consider the trivial vector bundle over X with fiber G. Then I can look at the fiber of Borels, fiber bundle of Borels inside this trivial vector bundle. Over each point X, I have the pair X and some point in B of X, where B of X is the Borel corresponding to that point. And inside B, we denote by N the sub-bundle of B consisting of nilpotent radicals, these B's. So N of X is a fiber of this, and this is the commutator of B of X, B of X. So then I can look at H, which is the quotient of B mod N, and B and N are clearly homogeneous bundles for the corresponding algebraic group G. So H is such too, and H, I mean, from conjugacy theorems, you know that H is a trivial G bundle. So I will denote by H the global sections of the sheaf of sections of H. And this is what I call abstract Cartan algebra of G. And then for any X in B of X, in X, the flag variety, I can look at the Borel subalgebra B of X. Inside it, I can pick a C, which is Cartan subalgebra of G. And then I can look at maps C into B of X, which I mean maps onto B of X mod N of X, which is a fiber of our trivial vector bundle. So there is only one global section which pass through this, so we have a natural isomorphism with H. So this gives us, if we fix an X and the Cartan in B of X, a natural isomorphism of that particular Cartan, with subalgebra, with abstract Cartan algebra, and then we can look at dual map, which goes from C star, from H star into C star, which we call specialization at the point X in X. So this is used to label the parameters. This specialization has the property that I can look at the root systems G of G with respect to C, and any such root system is of course, in C star, and by specialization, it's identified by a root system in H star, which I will denote by sigma. And this is the abstract root system of G. And again, conjugacy theorem says that for any C, you get the same root system. There's isomorphism with sigma. Now, I know that Kari will object. I will take the system of positive roots to be the system which corresponds to n x's. I mean, he and Wilfrid wanted that we follow geometers and take the opposite one. I do not like my Verma modules upside down to be the lowest weight. And so, and the formulas we are used to in representation theory, at least which I learned before localization, look more familiar. Anyway, the transition is very simple.
I will request.
Okay. Yeah, I mean, we can have an ideological discussion about the role of -1 in mathematics at the end of during lunch. So for each lambda in H star, anyway, our main idea, the main idea of this workshop is to actually show that we should study the lambda modules, Harish-Chandra modules, instead of representations, and then this becomes irrelevant. The ordering appears just when we apply cohomology, and all the secrets are discovered before that, as they will explain to us. So, for any lambda in H star, Bailinson and Bernstein constructed d lambda x, which is a sheaf of twisted differential operators on X. So this means that, I mean, I don't want to go into precise definition. We discussed it in a course. So basically, locally, it looks like a sheaf of differential operators, but the glue is different globally. And it comes with a natural homomorphism of the enveloping algebra U of G into d lambda. And they prove in global sections, let's see. So the first thing one observes is that if I have lambda in H star, then the space of maximal ideal in Z of G by Harish-Chandra homomorphism is identify the quotient of H star by the Weil group W of sigma, this Weil group. And so if I take lambda, to lambda, I can attach the orbit of lambda. And this orbit of lambda corresponds to some maximal ideal I theta in the center of the enveloping algebra. So we define U theta is U of G modulo I theta U of G, and this map factors through this quotient, and the first result is that this map is an isomorphism. And the second result is that higher cohomologies of d lambda are 0. Now, let's use this. So we look at the category of quasi-coherent d lambda modules on X, and I have a function of a functor of global sections in the category of modules over the global sections of the lambdas. So this is U theta. And then I can define the localization functor delta lambda, which is just delta lambda of V is d lambda tensor over U theta by V. So this is the functor Dougal mentioned in the first talk. These two form an adjoint pair. So we have that home delta lambda of d lambda delta lambda V U, and U is some d lambda module, is to home U theta V the global section. So
Dragan, I should know this, but there's no anti-dominance assumption on lambda in the cohomology vanishing?
no, no. Actually, yes.
Yeah.
I mean,
Sorry, I forgot the course.
this is, we are going to prove this, but in a way, this vanishing follows. I mean, just to give you some, this is not the proof we are going to use. If you look at the corresponding grading object,
yeah,
it doesn't depend on lambda, and the higher cohomology vanishes, but some theorem about cohomology of O on the cotangent bundle, which is that gives this symbol cohomology vanishing. Yeah, I mean, they will give us better insight in all of these things if you put large stuff in it. So, yeah, I mean, this is exactly what I wanted to do first, differently than in the class. I wanted to keep arbitrary lambda. If
Dragan, could you continue over here, please?
oh, sure. Yeah, just tell me what to do. So lambda is regular if any dual root on lambda does not vanish. So I'm not in the walls of Weyl chamber. Under this condition, U theta has finite homological dimension. Therefore, localization functor has finite left homological dimension. And by formal reason, this gives us adjointness of corresponding derived functors. So if I denote by dB d lambda, derived category of M U C d lambda and the U theta derived category of M U theta. I mean, let me point out here that there is a theorem which requires a proof that this derived category of NQCD lambda is maps into derived category if we don't drop quasi-coherence, but assume just that cohomology are quasi-coherent. And this arrow, natural arrow, is an equivalence of categories. And this is important in proving D-module results, that we do not have to struggle with quasi-coherent things, but we can just deal with sheaves till the very end. This is important in a construction of, say, direct image functor for D-modules. And so we are going to discuss this in the class. So anyway, now we have the following situation, and dB d lambda, and we have derived functor of cohomology, R gamma, and du theta. And we have derived functor of localization, which goes in the opposite direction. In singular case, things go bad because U theta has infinite cohomological dimension. So we have to use complexes bounded from above, and things are not so nice. But this is what is good for our purposes. Now, let me point out that this tells us that, say, in the case of A2, when, I mean, we can look at lambda and some other W lambda, and if I look at dB delta W lambda, then again, I have these arrows which are equivalences of categories dB U theta. So what can I do? I can go from here, apply R gamma, and then localize the wrong place, W lambda, and I get a functor between these two derived categories. And this is so-called intertwining functor. And the point is that under some condition on lambda, this intertwining functor is given by a geometric formula. So we know how to do from here to here via geometry, and if there is time, I will discuss this later. And basically, we can. So one of the strategy of proving theorems is to use intertwining functors to reduce the question to some simpler D-module situation.
But Dragan, this is for these practicals.
Yes, yes. I mean, intertwining functor, when you write it down using geometry, is actually equivalence of these two categories independently of lambda. This is one of the things like I was joking before, that basically if we are on the level of D modules, things kind of work better.
And just more basically like that, those R gamma and L delta are also.
Yeah. I mean, we are going to discuss this in the class at some point. I mean, this is relatively formal. So this is the one of the first thing on the list, Dougal's list. I mean, he probably wanted that we do this more explicitly, but I will try to see if we can squeeze this late.
And Dragan, how should I think about these intertwining functors, for example, in terms of supports or something like that?
This is a very good question. We do not, there is nothing very deep we can say. They can behave in different ways. For example, if you look at Borel-Weil, intertwining functor in this case takes a line bundle, moves the parameter from lambda to W lambda, but it's again a line bundle. But since cohomology shifts in degree, intertwining functor also has to shift line bundle to the left if we increase the length. The important thing is that you can, if you take simple reflection, you can increase the support by 1 generically, and there is always a simple route where you can do this, except if you have full support, of course. And this is the way which we will explain how to get information about asymptotic behavior of matrix coefficients in Harish-Chandra modules corresponding to various D modules. This is related to Dougal's remarks about temporary representations. So, I mean, this is a, I think maybe
I'm allowed one more question. But,
yeah, sure.
Do these give you a braid group action? A braid group action?
Yeah. Mm-hmm. Okay, so now again, let me recall what we discussed in class. Yeah, I should put a theorem here that this is equivalence of categories. So now we had this definition as in the class, lambda is anti-dominant if alpha check lambda is not a positive integer for alpha check in sigma, alpha in sigma. And then
Sigma plus maybe?
Sigma plus, yes. Thank you. So under this condition, as we discussed in the class, we have a theorem that gamma is exact. And if in addition lambda is regular, then we see that MQC d lambda and U theta are equivalent, and equivalence is given by gamma in delta lambda. Basically, in this situation, global sections and localization factor are exact. The length, cohomological length of localization factor and gamma are given by the number of wall crossings you have to do to go from anti-dominant chamber to your position. So we can say more precisely how these factors behave. Okay, so this is basically where we more or less in the course. Now, the next step is what Dougal was mentioning. And so he defined Harishchandra modules, which are relevant for real groups. I just want to point out what is important for localization theory. So we have our G, and now we have a connected algebraic group A with homomorphisms, say phi in automorphisms of G, such that the differential is injective. So we say that, say, G and K are a Harishchandra pair. I mean, in the case discussed by Dougal, G was complexification of a real Lie algebra of the group GR, and K was complexification of maximal compact. I think you denoted it by KR. So then we can define the category of GK modules. K and corresponding M U theta K. So, and these are basically your G modules and K modules, and they are algebraic K modules. So the whole module is a union of finite dimensional invariant K invariant subspaces when K acts algebraically. And let me point out that I'm not assuming in the moment that K is reductive. I mean, K can be any such connected algebraic group. This works fine. And I can look at localized version of this category. So these are quasi-coherent D lambda K modules. So we call so they are K equivariant D lambda modules, where if I differentiate the action of K, I get the action of the Lie algebra K on our sheaf. And there is another copy of K which sits inside G, and G embeds in D lambda, and we want that these two actions are the same. And now, I mean, of course, this varies from paper to paper. I will say, in general, of course, we get in this situation, again, the theorem that these two categories are equivalent. I mean, with the derived categories, I mean, this is iffy because these are not good categories for homological algebra. So I will stay out of this. I mean, one has to deal with this in a different way. But, so this is, till this moment, not very interesting. It's more or less formal, but then let's call these So, okay, assume our group K maps, to morphisms of G. So it acts on the flag variety. Just K moves around the Borel subalgebras in G, and assume that K has finitely many orbits in X. And consider the category of the subcategory of MQC and call the lambda K, which are coherent. So as the lambda modules. As OX modules, of course, they will be quasi-coherent only. Then we can, this is what Jordi will talk about in the seminar in 2 weeks. Then in such situation, when we have coherence, we can define good filtrations on those modules and consider graded modules as modules of our graded sheaf of ideals, and we can introduce the notion of characteristic variety. And if we have finitely many orbits, the characteristic variety will always have minimal possible dimension, which is just dimension of the flag variety, and these modules will be holonomic. So this is the first simple result, that these are holonomic as the lambda modules.
The equivariance forces harmonicity.
Yes, because basically you can, roughly speaking, this module will have K equivariant coherent filtration as OX modules. So these pieces under the action of Lie algebra K will stay put. So on the graded object, K will kill those, and this will give you an ideal which is sufficiently big to force characteristic variety to be small.
Well, that's in other words. This K covariance forces the characteristic variety to lie on the union of the proton.
Yeah.
The orbits. Because you're going to find many events.
Yes, exactly. So this is and of course, basically what Dougal and Curry will explain to us that they have some canonical good filtration, which is more useful than at least in the cases we are interested in. So one fantastic consequence of this is, it's very easy to show that these categories are Noetherian and Artinian, so objects of finite length. So this implies that in this case, by equivalence of categories, that in this category, the objects have finite length, if this condition holds. Of course, it's a very old results about algebraic group actions that in case Dougal described, there are finitely many orbits. So we know that Parishchandra modules in his sense have finite length. Also, it's important to observe, because of the people in the course, that holonomicity is local property. So we need to consider only this for untwisted differential operators. If we understand the situation there, then we understand it in general. And we are going to call objects in this category Harishchandra sheaves. Okay, so now why is this nice? Because we can easily describe irreducible. I mean, these modules are Harishchandra sheaves of finite length. So to understand, at least in some sense, the category K group, we need to understand irreducible. So we can discuss classification. So let's assume that V is an irreducible Harishchandra. Then, so now if you read Slack of the course, there was this discussion of the support. And I like the definition. Jordi mentioned two definitions, and I prefer the one where support is closed by definition. So the complement of the largest open set where the restriction of D module is 0. So if we agree with this, then support of V is a closed algebraic subvariety of X. And of course, because of Harishchandra, of group action, it is K invariant. So now if you think about this for a moment, you see that this is a closure of a unique orbit of the group K. So if I have an irreducible Harishchandra sheaf, we attach to it a K orbit, Q. Now, what do? We look at this Q bar, and this is Q union with some junk in the boundary, which are just finitely many orbits. So let's take the flag variety and throw this out. So X, I call this X prime. Then Q is a closed subvariety and smooth. And again, an elementary exercise is that if I take an irreducible D module and restrict it to an open set, in this case to X. Sorry. Sorry. Yes, I understand. I'm just forgetting. So there is this nice property of D modules, algebraic theory of D modules, that if you restrict an irreducible D module to an open set, you either get 0 or something irreducible. So I take V and restrict it to X prime. This cannot be 0, so it's irreducible. And this is a D module on X prime, of course. And it's also K equivariant if you want. And it's irreducible because it cannot be 0 because of the way how we picked X prime. So then there is a following basic result of Kashiwara, which we are going to prove at some point, which is very easy, especially if you were ever played with D modules, with Verma modules. If you have a smooth closed subvariety in another algebraic variety, at the moment X is arbitrary smooth variety, then you can define a functor from D modules on Y to D modules on X. Basically, formally, you add derivatives in normal direction. And of course, and then there is a restriction factor Jordi talked about, I think, in this seminar, which goes back. And Kashiwara's theorem says that direct image factor from D modules on Y to D modules in X supported in Y is an equivalence of categories. And it preserves coherence and holonomicity, and so basically this implies that this V lambda V restricted to X prime is direct image. So J is an inclusion of Q and X prime, J plus of some D module with a twist. And if you fiddle with this, you figure out how to describe this. So, which is, so this is holonomic D module on Q. And the support of this D module is called Q. It has to be holonomic. So by the stuff Jordi will talk in 2 weeks, its characteristic variety have to contain zero section because the support is everything. And so the zero section in cotangent bundle is inside, but
that's the B zero.
Yes, exactly. So generically, it has to be zero section because of holonomicity. Otherwise, dimension would be bigger. But because of equivariance, it has to be zero everywhere. So this tells us that this is a connection in a sense of D modules. So this is coherent OX module with D module action. And of course, it has to be reducible. So the representation on the stabilizer has to be irreducible representation of the stabilizer. So we know what tau has to be. Tau is a connection on the orbit Q. So to any reducible Harishchandra sheaf, we attach these, say, geometric data, an orbit, and an irreducible equivariant condition with a condition on the stabilizer on this orbit. Now, what I can do, we can now look at inclusion I of Q into X. This I is the composition of J and the open inclusion K of X prime into X. Again, one result I hope we can prove at some point is that direct images preserve holonomicity. So this tells us that I plus of tau is holonomic, the K equivariant. So it's basically is in MQC delta lambda K. On the other hand, if we, since direct image of K for open inclusion is just the standard sheaf theoretic direct image, and its adjoint is the restriction, so we see that Y on X prime is the same as I plus tau on X prime, what is the same as J plus tau. So by this adjoint result I just mentioned, we see that V maps into this I plus tau, and this is the unique, the image, irreducible sum of this direct image. So we introduce the following notation standard Harishchandra sheaf attached to geometric data q tau is, so is this thing is I q tau is I plus of the connection tau, and it has L q tau as unique, irreducible sum. And the theorem is that this gives us a classification of all irreducible Harishchandra sheaves. So L q tau are all irreducible Harishchandra sheaves, and L q tau is isomorphic to L q tau prime if tau is isomorphic to tau prime as connections on the orbit. So this gives us the classification of all irreducible objects. Now, the consequence of general nonsense we discussed before gives us the geometric classification of Harishchandra modules. If lambda is antidominant and regular, global sections of these Harishchandra sheaves are irreducible Harishchandra modules. And they're isomorphic if and only if geometric data are the same. So what happens in a singular case, so if lambda is antidominant but not regular, is that there are two options, and there is a precise criterion for this. Either the cohomology of LQ tau vanishes in all degrees, or it's non-zero and then it's irreducible. So basically, as you saw in the case of Borel-Weil bot, or say Borel-Weil, on line bundles are just, since K is transitive, so acts on a whole flag variety, your connection is your D module itself, and it has to be reducible, so it has to be an invertible OX bundle. And if lambda is regular, it will give you a finite dimensional representation of your group. If it's singular, you will get the global sections vanish. So exactly you get what you would expect. Okay, so this gives us a classification, and my time is almost up. Okay, so now let me just say a few words very vaguely because this was on Dougal's list. So what happens? What are the parameters of tau? As I said, we look at the stabilizer. The stabilizer is, okay, now I'm being vague. So is basically intersection of K and the Borel corresponding to that point. So the lambda parameter, which gives the twist, vanishes on n. So the lambda parameter is determined by the piece of Cartan sitting in K. If K is given, like in a case of real group, as a fixed points of Cartan evolution, then we can choose always a Cartan which is preserved under Cartan involution. So we have your Cartans and abstract Cartans for the Q orbit splits into direct sum of the eigenspaces plus and minus one of the Cartan involution. And if you do the calculation, which determines the twist of the connection is restriction of lambda to the split part of the Cartan, the one corresponding to eigenvalue minus one. And if you look at lambda and restricted area, it's a real part, this determines how the asymptotics of matrix coefficients at the infinity behaves. I mean, I have no time to, okay, if people are not objecting, I think I can explain in SL2 what's going on. Take 2-3 more minutes to get the flavor of the result, because I think Google will need this, say in SL2. So basically the D module background of the picture Google was talking about. So these are my orbits. So we have the action of C star on a flag variety. You have 2 fixed points and an open orbit. You can think of C star. And the D modules corresponding to closed orbits are just have a simple structure, and they correspond to discrete series. For those things, the condition means, in this case, the Cartan involution acts on the Cartan with +1. So basically, lambda has to be a character of the torus, and this gives the integrality condition. On the open orbit, actually the stabilizer doesn't contain anything from the Cartan, and the Cartan is the Cartan involution act on it by as -1, so this is the vector part. There's no condition there. So we have Harish-Chandra module for all lambdas, and the global sections are principal series as lambda varies. This is basically the picture described. If lambda satisfies corresponding integrality condition, then the monodromy around these points in D modules corresponding to the open orbit, to the standard D modules, is gives us that there are section which extends over the point, and we get inside the D module, we get a line bundle and a quotient in some standard module attached to open orbit, and the quotient gives us 2D modules in these 2 points. And this gives us, if you apply gamma, finite dimensional representation by Borel veil and 2 discrete series in the quotient. I mean, a nice exercise, if you want to think about this, is to consider higher covers of SL2, where actually in SL2 by accident, the monodromy here is all are the same. If sections extend here, they extend there. But this is just a fluke. If you go to higher covers, then you will have some representations where things extend at one point and not at the other point. And the other thing is that these results related to the asymptotics imply that tempered representations, so representation it's kind of mildly decay at infinity, depending how you, they correspond to the lambda parameter, which is purely imaginary on the vector piece of the Cartan subalgebra. For example, square integrable representations, which behave even better in the temper. In this case, we must have compact Cartan. So, and this is what Harishchandra already proved. And also, infinitesimal character has to be regular, and to each closed orbit we attach a discrete series. So this picture holds in general, and this is exactly Harishchandra's characterization of discrete series. And I mean, this is what I hope we can discuss later, I suppose. Okay, so I will 5 minutes over time.
Thank you, Joe. Stop saying my face is a joke. Question, so if I take something anti-dominant, the localization is an equivalence, and then I can imagine moving it onto a wall, and so it becomes non-regular.
Yeah.
And now my localization function kills certain simples, and the others become irreducibles. And I guess this is exact.
Yeah.
And so it's a quotient function.
Yeah. Exactly. Yeah. This is you get quotient value of the D modules by the D modules you know cohomology at all. Stuff you don't see cohomology. And this is what pays our food. If this is not the case, we will be out of business long time ago.
So just a remark that this is kind of like, this often happens also in modular representation theory, that you have some category of interest, for example, representations of symmetric groups or something, and then you have some category living over it, and a quotient function coming down, and this category is finite global dimension, and this category is infinite global dimension. So it's like a kind of resolution of singularities in the division.
This analogy is very mysterious.
And one other question is there a classification of what you were calling Harishchandra pairs?
I think the answer is yes. There are papers of a bunch of people doing algebraic group. One name I remember is Brion, and they talk about the spherical varieties, and so I think it's known which groups are involved.
Okay. Is it the same thing as G mod K being spherical?
I think it basically reduces. Yeah, I think you're right. Yes.
So what was the conditional decay actually being a hard time of that?
I mean, this depends. Here, I didn't assume anything. I just said Harishchandra sheaves if there are finitely many orbits, but I could say that this is a Harishchandra. There are finitely many orbits. It's just if you don't have finitely many orbits, nothing exciting happens. If you have finitely many orbits, this is forces the polynomicity, and then you can.
Well, maybe it's too exciting.
It's really exciting.
Yeah. I don't know.
A little too exciting for me.